Hi there, it's Miss Heaton. Today we're going to be talking about the periodic table and ionic bonding. These sections written down here at the bottom correspond in your Honors Chem textbook to the entire unit that we're about to start. I didn't break it down by exactly what we're talking about today, but if you need more help, please check your textbook in those sections. We're going to start by looking at the periodic table. Hopefully in class you got a blank periodic table to fill in as we go through this. If not, you could find one online or just write this on your periodic table. The first breakdown we want to do is break the periodic table into metals and nonmetals. As you can see here, metals are listed in pink. All of these elements are considered metallic, so they're malleable, lustrous, which means shiny, ductile. Ductile and malleable basically both mean that you can bend them, and they conduct electricity and heat. The yellow ones are the nonmetals. These are usually gases or solids. They're brittle, so if you try to bend them, they break. They don't conduct heat and electricity. And then the elements along the stair-step line, which actually goes down here as well, the metals along that stair-step line are called metalloids or semimetals. You can see both those words here, semimetals and metalloids. And they're kind of in between in terms of their properties. That's the dividing line between metals and nonmetals. They tend to be semiconductors, which means that they're used in computer chips, like silicon computer chips. The rest of these are used in that as well. Okay, the next breakdown is the groups and periods on the periodic table. The periods are the horizontal rows on your periodic table. They are numbered 1, 2, 3, 4, 5, 6, 7, which correspond to the main energy levels of that row. Except for, remember, the D's are off by a row and the F's are off by 2 rows. The vertical groups actually have more in common. So each column here represents a different group, and these groups tell you a lot about the elements within them. They tend to have similar properties. Their electron configurations, as you can kind of see here, all end in the same configuration, and that's why they have similar reactivity and similar properties. And they also have similar numbers of valence electrons. Let's look at this word. This word just means the outer electrons. And those are going to be really important today when we start talking about ionic bonding. The valence electrons include only the S and P electrons. So like this element right here, which I don't have labeled, that's phosphorus. It has 1, 2, 3, 4, 5 valence electrons because it has 5 electrons in its third energy level. We're going to talk about that more here in just a minute. What we're going to do now is label each group on the periodic table with a different color. The alkali metals are this column over here on the far left. These tend to be very reactive. If you want to see something really fun, Google alkali metals on YouTube. You can see some good explosions there. The second group we're going to talk about are the alkaline earth metals. I'm going to color those here in orange. These tend to be a little bit more stable. They have 2 valence electrons, and they are also very commonly found in the earth. A lot of rocks contain calcium, magnesium, barium, strontium. These are also very essential to life. Let's get another color going here. Let's get some green going. We're going to jump over here to the halogen group. This green column is the halogen group. This is where you find fluorine, chlorine, bromine, iodine. These elements are used in purifying things. They have 7 valence electrons, so they are almost as stable as the noble gases. This purple column here is the noble gases. We've already talked about these a little bit with our electron configurations. Remember, everyone wants to be like a noble gas because they're very stable. And the reason is that they have a full p orbital. Their valence shell is completely full. Another important group to note is the transition metal group. Let's color them in blue. So the transition metals are the D blocks. So the D block on your periodic table is a transition metal. And these are the metals that we tend to think of as real metals. You know, we've got chromium, silver, gold, copper, nickel, iron. All those traditional metals are transition metals. And the inner transition metals, I think I've mentioned that word before, the inner transition metals fit inside of the transition metal group. So the F block are called the inner transition metals. A lot of these are synthetically made. They don't occur naturally. Most of them are radioactive. just to kind of reiterate here, let's get the stair-step line going on. This stair-step line, again, divides the metals from the nonmetals. And anything that has like two sides touching that line is a semi-metal or a metalloid. So these elements down here are also metals. They're kind of other metals. They kind of act like transition metals. And then these elements up here are also nonmetals, that their groups kind of do different things, so we won't name them. Okay, let's talk a little bit more about these valence electrons. Remember, valence electrons are the outermost electrons. So we're going to label each column with the number of valence electrons that it has. This first column, the alkali metals, has one valence electron. You see just one electron in the s orbital. The second column has two valence electrons. We're going to skip over here to the third column. We're going to skip the d's, go straight over to the p's. This column has three valence electrons. 1, 2, 3. This column would have 4, 5, 6. The halogens all have 7, 5 p's and 2 s's. And then the noble gases have 8. We're not going to worry about the D or the F blocks for valence electrons. Now, this kind of goes into ionic charges, which is what we're going to do next. Ions form so that an element can be like a noble gas. So let's write the ionic charge that each column will form. So if this column right here has one valence electron, what's going to be easier? Well, actually, let's pick this element here. Is it going to be easier for this element to lose its one electron and become like the noble gas before it? Or is it going to be easier for it to gain 1, 2, 3, 4, 5, 6, 7 and end up like the next noble gas? Obviously, it's going to be easier to lose one electron. So if it loses one negative charge, it's going to become a charge of positive 1. The same kind of thing happens for column 2. They'll form plus 2 charges by losing by losing 2 electrons and becoming like the noble gas before them. Let's jump over to the halogens. They tend to form -1 ions because they have 7 valence electrons. If they get one more, they're like a noble gas, which makes them very stable. Oxygen's column tends to form -2 charges. Phosphorus tends to be -3. We could say that aluminum right here tends to be +3 as well. The other things in that column do weird stuff. And then this column here, the carbon column, also does weird stuff. We'll talk about that later. But those are the important charges to note on your table. Okay, let's talk a little bit about trends in the periodic table. The first trend I want to talk about is atomic radius. Because they have similar properties within a group and period, they will tend to have similar trends, but they will vary periodically. That's kind of how the periodic table is arranged. So the radius is telling you how big the atom is, and atoms tend to get bigger as you go to the left on a period and as you go down a group. And the reason for that has to do with a couple different things. Within the period, so within that row, as you go across, there are more and more protons. So the more protons there are, like sodium has 11, magnesium has 12, aluminum has 13. The more protons there are, the more that positive charge is going to pull in on the electrons around it. And so the atom's going to get smaller and smaller as those protons pull the electrons in. As you go down a group, what's happening? Well, they all have the same number of outermost electrons, but their last electron is getting put in a further and further out energy level. And so the further away it is from that tiny little nucleus in the middle, the larger the atom's going to be. Okay, the second trend is ionization energy. This is the energy needed to make an ion. So it's the energy needed to take one of these electrons and completely remove it. And this trend is the opposite. It increases as you go up and to the right on the periodic table, the opposite of atomic radius. And here's why. Because basically the bigger the atom is, the easier it is to steal an electron from it. Because if that last electron is far away from the nucleus, it's going to be pretty easy just to take it off and make it into an ion. So generally, as you go down a group, there's going to be more and more shielding. So as we're talking about going down a group on a periodic table, remember the electron gets put in further and further out energy levels. So the further away that electron is from the nucleus, the easier it's going to be to steal it. And also, because it's further away, there's more electrons in here shielding that outermost electron from the positive nucleus. So because these negative electrons are kind of hiding the nucleus from the outermost electron, it's easier for that electron to walk away when you add some energy. As you go left to right on the periodic table, you are again adding more and more protons. And remember, the more positive charge there is, the tighter that atom has hold on to its electrons. The third and final trend is electronegativity. It's very similar to ionization energy in terms of its trend. It goes up and to the right. But the difference is that the noble gases have no electronegativity. And this is why. Because electronegativity is how likely that atom is to attract electrons to itself when it bonds to another element. So like if bromine and oxygen are trying to share some electrons, oxygen has a greater electronegativity because oxygen is here versus bromine being right here. Since oxygen is closer to the top right, it has a greater electronegativity. So it's going to pull electrons more towards itself. The reason this happens is very similar to ionization energy. As you go down a group, there's less likeliness for those electrons to get pulled towards the element because there's more shielding. Those electrons are kind of hidden from the nucleus, so if another electron came in, it would be shielded from the nucleus by these inner electrons. Also, as you go across a period, you're adding more and more protons, which are going to increase the likelihood that that nucleus is going to be able to attract more electrons to itself. Okay, take a minute here to check yourself. Follow the trends on the periodic table to identify which has a bigger radius, a smaller electronegativity, and a bigger ionization energy. If you want more information, you can check out this YouTube video. It's awesome. It talks about gangsta thug atoms and shriveled old lady atoms. That'll help you remember the trends.